Hello students, in this video I am going to discuss the particle classification. Basically there are two types of particles, elementary particle and composite particles. We have already discussed elementary particles. Now we will discuss composite particles in this lecture. Apart from this, I am going to discuss strangeness quantum number, isospin quantum number, Z component of isospin, and the conservation laws or the conservation laws. Basically both type of conservation laws, exact conservation laws as well as approximate conservation laws, to find out that either the given interaction is weak, strong or electromagnetic, so that we can decide which type of interaction is involved in the given equation. So if we talk about the particle classification, then all the particles can be classified into two types. One is, first type of particles is elementary particles. First type of particles are elementary particles. And second type of particles are composite particles. Second type of particles are composite particles. These elementary particles, they are of three types. We have discussed in earlier lecture that these elementary particles are of three types: leptons, quarks, and interacting bosons or exchange bosons exchange bosons. We have already discussed all these three: leptons, quarks and exchange bosons. Now come to composite particles. Basically composite particles is made up of two types. One is mesons and another is baryons. Both mesons and baryons, they are known as hadrons. Hadrons. So basically hadrons are made up of two types of particles. One is mesons and another is baryons. Now baryons itself has two types of particles: nucleons and hyperons. So this is a total classification of the particles. Here we have already discussed leptons, quarks and exchange bosons. Now in this lecture I will discuss mesons, baryons, nucleons and hyperons. So we are going to discuss all these particles. Now come to mesons. First we are going to start with these mesons. So basically mesons are a part of hadrons. Mesons are a part of hadrons. These mesons are strongly interacting particles. They are bosons. These mesons. So mesons are number one, they are strongly interacting particle. They are strongly interacting particle. They are strongly interacting particles. These mesons are strongly interacting particles. Their spin is zero. Spin is zero for meson particles. If you talk about their spin and parity, then this is 0 minus. Parity is negative for meson particles. Spin is 0. So they are bosons. So these mesons are bosons. Their parity is odd. Their parity is odd, their spin is 0. So basically, if we divide these, if we classify these mesons, then first type of meson, so here I am writing particles, meson particles. So first one is pi meson. Pi meson. In this category, basically there are two type of meson. This is pi plus and pi naught. These are two type of pi meson. There are k meson. Another is k meson. K meson is k plus and k naught. And next is eta meson. Eta meson is neutral meson. This is eta naught. So these are the meson particles. These are the meson particles. If you talk about their spin, and parity, that is 0 minus. For all these particles, this is 0 minus. 0 minus is the spin and parity of these. If you talk about their lepton numbers, lepton quantum number, because these mesons are not leptons. They are not leptons. So their lepton number is 0. There is one more quantum number that is known as baryon quantum number. These are mesons. They are not baryons. So due to this reason, their baryon number is also 0. Their baryon number is also 0. I am just giving you a hint because they are not leptons, they are not baryons, they are mesons. They are separate type of particles. So these numbers are 0. These numbers are 0. Now, next is strangeness quantum number. Next is strangeness quantum number. So here, only these k meson, this k plus and k naught, they have plus 1 strangeness number, because they are strange particles. Both this k naught and k plus, they are strange particles. What is the meaning of a strange particle? After some time I am going to discuss. But here their strangeness quantum number is plus 1 for this k meson. So basically these are few important properties. These are few important properties of these mesons. Now come to anti-mesons. Antiparticle. If you talk about pi plus, its antiparticle is pi minus. If you talk about pi naught, its antiparticle is pi naught bar. For k plus, antiparticle is k minus. This is k naught bar and this is eta naught bar. This is eta naught bar. These are antiparticles. If you are concerned about their spin and parity, if you want to write down, then these are mesons. For mesons, for antiparticle, in case of meson, for antiparticle, basically in case of mesons for antiparticle, basically this will be minus here. This is minus, so it will remain minus. Parity is not going to change. This will be 0 minus, 0 minus. This will be 0 minus, 0 minus. This will be 0 minus. So parity is not going to change in this case. Now, if you talk about other quantum numbers, so basically L and B quantum numbers will be 0. As far as this S, strangeness quantum number, is concerned, for this K minus, this will be minus 1. For this will be minus 1. For other, this strangeness quantum number will be 0. So this is the total list of the mesons. So this is all about mesons. Now come to next type of particles, which are baryons. Now come to another type of particles, baryons. Baryons. Baryons are itself classified into two types of particles. First is nucleons. It is made up of two types of particles. First is nucleons. In nucleons, we have basically nucleons are the particles which are present in a nuclei, which can be present inside a nuclei. So there are two types of nucleons, you are aware. First is proton. It is represented by P. Another is neutron. So this is represented by N. If you talk about neutron, its lifetime is nearly 933 seconds, while these protons they are stable particles. As far as spin and parity is concerned, so spin and parity is concerned, this is 1/2 plus. So if you want to write spin and parity, this is 1/2 plus. Because these are baryons. They are not leptons. So this L number will be 0. And because they are baryons, their B number will be 1. Strangeness quantum number for these will be 0. Here. And if we talk about the antiparticles, basically here antiparticle will be P bar and this neutron will be N bar. As far as spin and parity, their spin will be opposite. If spin of this is half, then for this case spin will be minus half. You can also write this as half, but basically spin of this will be minus half and this will be negative. So if in an equation we are taking the spin half for the particles, then for the antiparticle this will be minus half. This spin will be minus half. And parity will be opposite to the particle. So parity for the particle is plus and here parity will be negative. If you come to the case of leptons also, in case of leptons, parity and spin was 1/2 plus. In that case, when we were writing this spin and parity for antiparticles, we have written that 1/2 minus. Even in that case, spin is minus 1/2. And parity is opposite to the particles. So here, their spin and parity is very similar to the leptons, but these are nucleons. They are heavier particles as compared to leptons, as well as they are strongly interacting particles. Here, these nucleons, they are present inside the nuclei and they are strongly interacting particles. They are strongly interacting particles. Now come to another type of particles, that is hyperon. Second type of baryons. Are hyperons. They are strongly interacting particle. They are strongly interacting particles. Here I want to mention you one thing, that all these mesons and baryons, either nucleons or hyperons, basically they have a quark structure. They are made up of quarks. That's why truly they are not elementary particle. They are known as composite particle because they are made up of quarks. Now again come back to hyperons. So basically these hyperons are strongly interacting particle, and they are also unstable. They are also unstable particle. They are also unstable particles. They are produced. These particles are produced as a compound state of nucleons and mesons. So these hyperons are produced as a compound state, as a compound state of mesons and nucleons. They are formed as a compound state of mesons and nucleons. Another important aspect of these hyperons are that they decay. These particles decay via weak interaction. And during this decay, they produce their end product. One of their end product will be nucleon. They decay via weak interaction, and one of their end product will be nucleon. As far as their list is concerned, first particle, here I am drawing the list for these particles. So here I am writing first, I am writing particles. So the first particle is lambda. This is known as lambda. Here I am writing here. This is known as lambda. So first particle is lambda. Second is sigma particles. There are two types of sigma particles. Second is sigma particles, sigma positive and sigma naught. These are two sigma particles. Third is cascade particles, cascade negative. Here this is cascade negative, or you can say here sigma. Basically before sigma, this is sigma plus, I forget one to write down, sigma plus, sigma naught and sigma minus here. And we have then cascade. So cascade negative, so basically this is the sign for cascade negative, cascade neutral and omega. This is omega negative. So this is the list of all particles which belong to this hyperons, As far as spin and parity is concerned, J pi, their spin is half plus, this is half plus, this is half plus, this is half plus, and this is half plus, this is half plus. Only for this omega minus, this is 3/2 plus. So parity for these particles is even. These are even parity particles, and spin is half and 3/2. Spin is half and 3 by 2. These particles are hyperons, they are baryons. So their L number is 0. L number for these particles is 0. They are all baryons. So their baryon number is 1. Their baryon number is 1. They are also strange particles, so they have some strangeness quantum number. This is -1, this is -1, -1, this is -1, this will be -2, -2 and -3. These are the strangeness quantum number for these particles. After this, we have antiparticles. We have antiparticles. We have antiparticles. Spin will be -12. Their spin will be -12 for all these particles. -12. And their parity will be opposite to this. Parity will be negative. Parity will be negative. Parity will be negative. And how these antiparticles are represented? For this lambda, we will represent this as lambda naught bar. This will be sigma minus bar. This is sigma naught bar. This is sigma plus bar. This is cascade positive bar. This is cascade naught bar. This is omega plus. And this bar, basically bar is representing here that they are antiparticles. They are antiparticles. So basically these are the spin parities, L number, B number, S number for these. L number, B number and S number for these particles. So this is a complete list of baryons. We will need these particles later on when we will have an equation and we have to find out, we have to decide that either a given equation is strong interaction, weak interaction, or it is electromagnetic interaction, or even we can also show that with the help of conservation laws that even that reaction is either possible or not. We can also find out that the given reaction is either possible or not. Here I think in the last row we are not able to observe this omega. So basically here now you can observe the last line. This is omega minus. Its spin and parity is spin is different. This is 3 by 2. This is 3 by 2. So you have to remember this. Its spin is a little bit different from others. For others, spin and parity is 1 by 2 plus, and for this, spin and parity is 3 by 2 plus. These are the L number, B number, strangeness number and antiparticles of this. Here I have wrongly written for this antiparticle. So this will be 3 by 2 minus. So you should be careful. You should be careful about the spin and parity of this omega particle and its antiparticle. As far as spin, as far as strangeness number is concerned, strangeness number for these antiparticles will be opposite. This will be +1, this will be +1, this will be +1, this will be +1, this will be +2, this will be +2, and this will be +3. These are the values of the strangeness quantum number for all these baryons. So in this way we have discussed all type of particles. We have discussed exchange bosons, we have discussed leptons. In case of leptons, you have to remember that I have written for leptons that for anti-leptons basically I have written their spin and parity as 1 by 2 minus. Actually this is 1 by 2 minus, but spin here in this case spin is 1 by 2 minus 1 by 2. This should be minus 1 by 2. So you can make this consideration when you will use the spin and parity in case of leptons. Now come to quantum numbers, which are useful, which will be very useful when we will decide the type of interaction. If we want to decide the type of interaction, then we have to find out, we have to take the help of conservation laws, and many of the conservation laws are based on these quantum numbers. So first quantum number that I want to mention is lepton number. So the first quantum number is lepton quantum number. So lepton quantum number. Lepton quantum number. Basically, this quantum number is used. This is used to differentiate leptons from another particle. If a particle is a lepton or antilepton, then for that particle, lepton number will be plus and minus 1. For other particles, lepton number will be 0. So basically, lepton number can have 3 values. Lepton number can be plus 1. For which particles lepton number will be plus 1? This will be for electron. This is for nu e, neutrino, electron neutrino. Then for muon, then mu neutrino, tau particle, and for nu tau. For these particles, lepton number will be plus 1. These are all leptons. They are all leptons. So for these particles, lepton number will be plus 1. It will be minus 1 for anti-lepton. So this will be E plus. This will be nu E bar. This will be mu plus. This will be nu mu bar. This is tau plus. And this is nu tau bar. So for anti-leptons, this lepton number will be minus 1. And it will be 0 for mesons and baryons. For all mesons and baryons, this quantum number will be 0. This quantum number will be 0. This is a very important quantum number. Basically, lepton number should always be conserved. Should always be conserved. If in a given reaction, lepton number is not conserved, it means that reaction is not possible. If a reaction is given, if an equation of a nuclear reaction is given, and suppose lepton number is not conserved, then that reaction is not possible. So basically, conservation of lepton is the exact conservation law. Conservation of lepton number is exact conservation laws. This is exact conservation law. This is exact conservation law. So this is first type of quantum number. Second type of quantum number is baryon quantum number. Next quantum number that is also that also follows exact conservation law, that is known as baryon quantum number. So another quantum number is baryon quantum number. Baryon quantum number. Baryon quantum number is represented by capital B. Baryon quantum number is represented by capital B. This is represented by capital B. It will be positive. It will be +1 for the baryons. It will be +1. Always remember, this will be +1 for baryons. It will be -1 for antibaryons, and for other particles it will be 0. Now, which particles are baryons? This is neutron. You have to remember this sequence. You have proton, neutron, nucleons basically. Then you have lambda naught, sigma plus, sigma naught, sigma minus, cascade negative, and omega minus. Oh, sorry, cascade neutral also. Cascade neutral is also there. And omega minus. These are all baryons. For these particles, this B number will be +1. This B number is going to be +1. For antibaryons, like N bar, P bar, antiproton, lambda naught bar, sigma minus bar, sigma naught bar, sigma plus bar, this cascade positive bar, cascade 0 bar, and this omega plus bar. They are all antibaryons. They are all antibaryons. And for these particles, this B number is -1. For these antibaryons, this B number is -1. For all other particles like leptons and mesons, leptons and mesons, leptons and mesons, basically this B is 0. This B will be equal to 0. So this is second quantum number. This baryon number must be conserved. If a reaction is possible, if a nuclear reaction which is given, if that is possible, then this baryon number must be conserved. Must be conserved. So baryon number will always be conserved, or must be conserved, or always. If a reaction is possible, then this B number will be conserved. If suppose B number is not conserved, then you will say that reaction is not possible. That reaction is not possible. So this baryon conservation law, this is also an exact conservation law. Exact conservation law. Conservation law. It is conserved. Baryon number is conserved in all three type of interaction. Lepton number, this L number and B number. This L and B number are conserved. Are conserved in all three type of interaction. Either strong interaction, it may be electromagnetic interaction, or it may be weak interaction. In all cases, basically these two conservation laws will be always followed. In all three cases, L and B number will always be conserved. They will always be conserved. So this is all about the baryon quantum number. Now come to another important quantum number, that is known as strangeness quantum number. Now come to another quantum number, strangeness quantum number. strangeness quantum number. This strangeness quantum number is represented by S. This is denoted by S. This strangeness quantum number is denoted by S. Actually, what was the need of this quantum number? Basically, the need of this quantum number comes into the picture when people find out few particles which are behaving in a strange manner. What type of strange manner? What type of strange manner I am saying? Basically, they are showing two important strange behavior. First, particles, basically this strangeness number, quantum number, belongs to those particles which exhibit following two important properties. What are the two important properties? First is they are produced, these strange particles, you can say these strange particles are produced via strong interaction. They are produced via strong interaction while they decay through weak interaction. This property is not exhibited by other particles. So this is one of the important property that is exhibited by these strange particles. Another important property is that these strange particles are always produced in pairs. Strange particles are always produced in pairs. These are two important properties of these strange particles. And the particles which behave in this way, they have some strangeness number. So here I am writing the name of the particle, and here I am writing their strangeness number. So first we will start with K mesons. K plus, strangeness number of this K plus is +1, and this for K naught meson it is +1. So both these K mesons, they have +1 strangeness number. Now come to lambda naught. Now come to hyperons. This is lambda naught. For this lambda naught, this will be -1, always remember. Then sigma particles, sigma plus, this is -1, sigma naught, this is -1, sigma minus, this is -1, then cascade negative, this is -2, cascade neutral, this is -2, and then omega negative, this is -3. So these are the values of these particles. Now if you talk about their antiparticles, if we talk about antiparticles, then it will be K minus, this will be K naught bar, this will be lambda naught bar, this will be sigma negative bar, this will be sigma naught bar, this will be sigma plus bar, this will be cascade positive bar, this will be cascade naught bar, this is omega plus bar. And what are their strangeness number? This is opposite to them. For these two it will become -1, for this particle it will be +1, +1, sign will change, +1, for this it will be +1, this will be +2, this will be +2, this will be +3. So these are the strangeness number of these particles. Other particles which we have discussed, other particles have zero strangeness number. Other particles we have discussed, they have zero strangeness number. Their strangeness number is 0 because they are not strange particles. As far as conservation of strangeness number is concerned, so this strangeness quantum number is conserved in strong and electromagnetic interaction. The C part is strangeness quantum number as S is conserved in strong and electromagnetic interaction. And electromagnetic interactions. So in case of these two interactions, this strangeness number will be conserved, will always be conserved. If suppose in a reaction, given reaction, strangeness number is not conserved, it means it will not be electromagnetic interaction and it will not be the strong interaction. This may not be strong or electromagnetic interaction. In case of weak interaction, this S number, the S number may not be conserved. S number may not be conserved. So in case of weak interaction, it's possible that S number is not conserved, but still there is a condition that change in S value, change in strangeness number will have only these possibility. It can change by only ±1. If there is a change in strangeness number in weak interaction, then this change will be only ±1. If change is coming ±2, ±3, then that is not a weak reaction. That's not possible. That reaction is not possible. So this is all about the strangeness number.